Okay. Yes, there are no bonus chickens. All right. So we need to go over today the start of Unit 4. Unit 4 is simple harmonic motion and waves. Okay, these two things go together because waves are usually caused by something that is oscillating with simple harmonic motion that is up and down over the same path repeatedly. Okay, so we're going to look at what simple harmonic motion is, how it can happen and be maintained, and understand how two common examples of simple harmonic motion work. That would be a mass on a spring or a simple pendulum. You thought this was just for circular motion. It's dual purpose. I'm saving the taxpayer all kinds of money by having this demo pull double duty. Okay, so I have a pendulum, okay, and it just swings back and forth. Okay, back and forth, back and forth. You are going to cluck like a boneless chicken. Not really. Okay, so it just swings back and forth over the same path. But in order for that to happen, something has to keep pulling it. Okay, what keeps making this thing move in this path? It has nothing to do with my hand. The weight. Okay, what force is weight? Gravity. Yeah. Okay. I mean, if I just have this like this, nothing happens. It's not a pendulum until I pull it away from its resting position. Okay. We call this resting position the equilibrium position because at this position, all the forces acting on the object are in complete equilibrium. The net force is 0 right here. As soon as I pull it away from equilibrium, gravity wants to do what? Pull it back. It wants to restore equilibrium. Okay? Now that's the weird thing about simple harmonic motion is that simple harmonic motion cannot exist without a restoring force, without a force that tries to restore equilibrium. The problem with all restoring forces, they fail and succeed and fail and succeed and fail and succeed and fail and succeed over and over and over again. Okay? They do succeed in bringing the object back to the equilibrium position. The problem is when it gets there, it just keeps right on going. Okay? Because it's built up all of this energy, then that results in it going the other way. Okay? So a pendulum continues to swing back and forth because that restoring force is constantly trying to restore the equilibrium that it was disrupted. Okay? Does that make sense to everybody? Okay? The same would be true if I had a mass on a spring. Okay? So if I had, like, let's say just a ball and it was on a big spring and I pushed it inwards, okay? What is the spring trying to do to me? It's trying to push back. It's trying to push that mass back to its resting position or its equilibrium position. If I let it go, the mass will go towards equilibrium, but all the work I did in compressing the spring is going to result in it building up all this kinetic energy, and it's going to go right past equilibrium. Once it goes past equilibrium, it'll start pulling on the spring, and the spring will start trying to now pull it back to equilibrium, okay? Which it will eventually do. Eventually the mass will stop on the far side and start moving back towards equilibrium again, and it'll pass right through equilibrium and start compressing the spring on the other side. That motion is identical forward and backward. Okay? It'll compress the spring as much as it'll stretch it on the other side. Okay? And that restoring force, if it's a perfect physical world, would just keep that thing oscillating forever. Okay? Obviously, in the real world, it comes to a stop because friction will convert some of the energy into other forms. All right, is that making some sense? All right, so if we have a playground swing, okay, it moves back and forth, it's a pendulum. Okay, you've all been on a playground swing before, okay? Somebody gives you a push, and off you go, okay? You start swinging back and forth. Now, eventually, again, that stops because this is the real world, okay? Unless you do what? Yeah, like you have to pump your legs, okay, in order to keep making the swing go. Basically, what you do when you're pumping your legs is you're putting a little extra tension in the chain of the swing. You always do it right at the top, right? The top of the swing, you kind of change the position of your legs, and it adds a little bit of extra force and tension to that chain, and it allows you to keep putting energy into the move. All we were talking about the mass on a spring. This is what it would look like here in the middle. Okay, so this would be my equilibrium position right here, the dotted red line. Okay, if I pull the mass to the right, I stretch the spring and the spring pulls the mass back towards equilibrium. If I let it go, it'll move to equilibrium, go right past it, and compress the spring on the other side. The spring will push it back to equilibrium. It'll go right through it, stretch the spring out on the other side. And just keep doing it. Okay? And also true for basically all musical instruments. Okay? Something has to be disturbed in order for it to start to oscillate with simple harmonic motion and produce a musical note. Okay? The simplest is the guitar string, okay, or any string instrument. Even a piano is a string instrument, okay, because it's hitting the strings on the inside of the piano. Okay? When you hit a string, basically what you're doing is you're pulling it away from equilibrium, putting elastic potential energy into the string, and the string tries to return to equilibrium. But it goes right past it, vibrates back and forth, moving the air beside it, producing sound waves. Yeah, it compresses and stretches and compresses and stretches the air surrounding the string, making the sound. Okay? All right. Everybody with me there? Making some sense? Okay. So in each case, there's an equilibrium position. So that's an important term that we have to know for the entire unit. Okay? Equilibrium position is where all the forces essentially add up to zero. Where the net force acting on the object is zero, and thus where it would rest. Okay? As soon as you pull it away from that position, a restoring force begins to act. In order for simple harmonic motion to occur, that force has to vary linearly with the displacement from equilibrium. Okay? So if I pull a guitar string 2 millimeters away from equilibrium, I would use, I'm just making up a number here, 3 newtons worth of force. If I want to pull it twice as far away, I'm going to have to use twice as much force, or 6 newtons worth of force. Okay? So for simple harmonic motion to occur, the restoring force has to increase linearly with displacement from zero. Okay? So equilibrium is always measured as zero, and then you have like a positive side and a negative side. Okay? All right, so the object is pulled away from the pulled away from its equilibrium position, in a force in the system pulls it back. Okay? That force can be gravity, as in the case of a swing or a pendulum. But here's the weird thing, and sometimes people notice this about gravity being a restoring force. Can gravity increase? Okay, then isn't what I just said all full of crap then? Because I just said that in order for simple harmonic motion to occur, the restoring force has to vary linearly with displacement, and gravity can act that way? Seems like I'm full of crap. Seems like I just contradicted myself. Okay? Except, here's what you have to realize. A pendulum swings in an arc. You're never going to have to calculate this. So you can sigh of relief. Okay? Gravity only pulls which way? Down. Okay? So when the object is here, gravity doesn't even pull along the path that it swings in. That's why there's no restoring force here at equilibrium. When the mass is out here, gravity's still pulling it straight down with the same amount of force it did here, or here. Okay? What's different is how much of that acts along the arc. It's a vector thing. Okay? The further away from equilibrium I get, like if I was like way out here at the horizontal, gravity acts right along the arc. So it would be 100% gravity. Whereas when it's here, only this component of gravity acts along the arc. When it's here, only this component of gravity acts along the arc. And that component gets smaller and smaller. And it's linear. Okay? You're never going to have to calculate that. Just so you understand, I'm not lying to you when I say gravity can do this, even though gravity doesn't get bigger. Okay? The force of gravity doesn't get bigger, but how much of it helps restore equilibrium does, because it's a vector. All right, but it's easier to see with a spring. And it's easier to understand that when I push on a spring, the further I try and compress or stretch the spring, the harder the spring pushes or pulls against me. Right? Okay? Some of you have ever jumped on like a pogo stick. Okay, it's not that common anymore, but yeah, okay. If you don't jump very hard, you don't bounce very much, okay? But if you push really hard, you compress the spring further, and the spring pushes back further, but it takes more force to compress the spring. Okay, everyone okay with that? Okay, so this is the important thing. It's what I was saying to you before. If the restoring force varies linearly with displacement, the motion that results is simple harmonic motion. Because the further away it gets, the harder the restoring force will pull, okay, until it stops the object. And the object starts moving back, okay? When it gets to equilibrium, it's moving really, really fast. So we'll go right past it and start making the restoring force pull back towards equilibrium in the other direction. But the further it gets away, the harder that restoring force pushes or pulls. Okay? If it's not linear, then you're not going to get simple harmonic motion. Okay? This is what usually occurs when you overstretch a spring. Okay? So if you had like a slinky, okay, and you had a mass hanging from it, and you were just having that mass bounce, okay, just a little bit, the spring can handle that. Okay? But if you get too far, you actually deform the spring, and the force stops being linear, it becomes exponential, and you'll ruin the spring. Okay? So it only occurs through a narrow range. Okay? Beyond that range, the force is no longer linear, and you no longer have simple harmonic motion. All right. Questions there? So the motion of objects that are oscillating, or sometimes they say vibrating or resonating with simple harmonic motion, can be described by two quantities, okay? Period and amplitude. Okay, now, period, we were already familiar with. We learned that term in the last unit. Period is the time for one cycle, okay? So for something that was orbiting or moving in a circle, it was the time for one revolution. In simple harmonic motion, it's the time for one complete oscillation. So that's out to one side, back through equilibrium out to the other side, and back to equilibrium, okay? It's got to go through equilibrium twice, okay, to be a full cycle. So what we're seeing here is, in fact, one full cycle. We're starting at equilibrium, we're moving out, okay, or down in this case, then we're going back to equilibrium, out above the line, and back to equilibrium. That is one complete cycle. What shape did I just draw? A wave. This is why simple harmonic motion causes waves. Okay? If this thing was sitting on the surface of the water and oscillating up and down, it would make waves. Right? That's the perfect wave. All right, so that is one complete oscillation. So the time it would take for that to happen is the period. This distance here and here are equal, and they are the amplitude of the motion. Amplitude is the maximum distance from equilibrium that the object will attain. Okay, so that's amplitude. Okay. Where have you probably heard the word amplitude before? Amps, yeah, okay. If you have an amplifier, okay, amplifiers increase the amplitude of sound waves. All right, so you want the amplifier that goes to 11. Not the one that goes to 10. You guys not seen? Okay, you gotta watch the movie Spinal Tap. It's all about this amplifier that goes to 11 and how that's better than the one that goes to 10. It's louder. Okay, so an amplifier, all it does is increase the amount the speaker making the sound is going to move. Okay, the more the speaker moves, the louder the sound it makes because it makes bigger waves, not longer, bigger. Okay, more amplitude, makes your eardrum move further. Okay, that makes sense to everybody? Okay, so amplitude has to do with how big the waves are. It also has to do with the energy that the waves or any other object moving with simple harmonic motion are going to have. Okay, Why would this have something to do with energy? Right, it's got some kinetic and potential energy. The further I stretch the spring, okay, remember I'm increasing my force over a greater distance, okay? So I'm putting more elastic potential energy into this spring the further I go, okay? So this is related to the energy of the object's movement because it's related to how much potential energy would be stored in the spring, okay, by the movement of the object. Now that potential energy gets turned back into kinetic, right? Because right here, the spring is neither stretched nor is it compressed. Therefore, it exerts no force, because we said the net force would be 0. There's no elastic potential energy at equilibrium. But there's lots of kinetic energy because this is where the object's moving the fastest. Once it goes past this point, it's going to start compressing the spring, which is going to slow it down. But it's going to do work on the spring and store potential energy in the spring, and then it's just going to keep doing that. It's just like a roller coaster. Okay? You go up and down, up and down, up and down on a roller coaster. Okay? You get gravitational potential, and then kinetic, and then gravitational potential, and then kinetic. Here, you get kinetic to elastic potential, to kinetic, to elastic potential, and to kinetic. All right? It's constantly converting those energies into each other. Okay, everybody okay with what amplitude is? Kind of how it relates to energy? We're actually not going to do much energy stuff till tomorrow. Not tomorrow. New test is tomorrow. We're going to do energy stuff on Wednesday. All right, so all simple harmonic motion is the same in principle. Okay, it all oscillates. It all has a period. It all has an amplitude, all of that kind of stuff. But what things can affect the oscillator are different. So if I have a mass on a spring, like I had in this question here, and it's on a horizontal surface, so it's just going back and forth, what are the two things that can affect how long it takes it to make that oscillation? Okay, let's say it's frictionless. Otherwise, yes, you're right, it would.
The mass of the block.
The mass of the block. And? It's something to do with the spring. It isn't actually length, but it's something to do with the spring.
So like the size of the coils of the spring?
It has to do with that as well. So it's about length, it's about the size of the coil, it's about the stiffness of the spring. Okay? If I do this operation and I've got the spring from like a clicker pen, like it's going to take a long time for that oscillation to happen because the spring isn't very stiff. It can be deformed a long way before it can stop that weight and move it back. Okay? Whereas if I hook this up to a car spring, it's going to oscillate like this. And the period will be really, really small because the spring won't move very much before it stops the weight, okay, and starts bringing it back. So the two things that can affect the period of a mass on a spring are the mass and the spring, or what we call the spring's constant. Okay? That is, how many newtons does it take to change its shape by a meter? Okay? We actually measure that in newtons per meter. Right? So mass and spring constant can affect the period of a mass on a spring. So this is our first formula in this unit. The period of a mass on a spring can be calculated by taking 2 times pi, multiplying by the square root of mass divided by spring constant. So, the bigger the mass, what happens to the period? Bigger or smaller? Bigger, yeah, okay. Like, usually we write it this way so it's not horizontal. Okay, but m is on top. That means as m gets bigger, t gets bigger, right? And the stiffer the spring, smaller the period, okay? Because the stiffer the spring is, the less it's going to move, or the less amount of time it'll take for it to stop the mass and start bringing it back to equilibrium. Okay, so those are the two things that can affect the period of a mass on a spring. Okay, so here's kind of a simple example. So I have a 0.20 kilogram mass attached to a vertical spring, okay, with a tension of 28 newtons per meter. So this is K, and obviously this is mass. Okay, the ball is released from its equilibrium position, how long does it take for the ball to complete one cycle and return to equilibrium? Okay, so that means we're looking for the period. Okay, so period is going to equal 2 pi times the square root of m over k. And I know both of those numbers. So it's just a matter of plugging them in. So 2 times pi times the square root of 0.2 divided by 28. Right? When I do that, I should get that the period of that movement is 0.53 seconds. So just over half a second for it to oscillate down and up and back. So that's pretty quick. 28 newtons per meter, that's a decent spring. All right, what if I need to manipulate this formula? What's that going to look like? Let's say I want to solve for either of the numbers underneath the root. What will my first step be? Square everything. Yeah. To get rid of the root, I've got to square everything. Right? So I would go t squared equals 4 pi squared times m over k. Now the root is gone. Now I can manipulate for either m or k. It's just algebra. Okay? The big thing people miss is that you have to square everything, and the most common mistake made is forgetting to square the numbers in your calculator. All right. Now, for a pendulum, okay, as we were saying, okay, different things can affect different oscillators. Okay, what are the things that could affect the period of a mass on or of a pendulum? Yeah, how long the pendulum is. So that's everybody always says. I've yet to have a class say to me that the mass matters. Does it? Gravity's the same for everything. Okay, so actually the mass of the pendulum makes no difference, and we're actually going to do a lab after Christmas where we'll prove it. Okay, we'll take pendulums of different masses, none of exactly the same periods. It's the strangest thing. Even though we can tell ourselves that that's the case, when we see those bigger masses, we just expect it to go faster, and it doesn't. Okay, so mass doesn't matter, but what is acting on the mass does. The acceleration due to gravity. Okay? This is actually how they confirmed on the moon what the moon's gravitational field strength was. They took a pendulum to the moon, simplest experiment ever, and just went, time it, okay, and let the pendulum swing back and forth, okay, figured out what the period of it was, knowing its length, and calculated the acceleration due to gravity on the moon. Now, obviously, they already had a pretty good idea what that was, or they wouldn't have been able to land there, okay, but it was a simple experiment to verify. All right, so similar formula, period equals 2 pi times the square root of L divided by G, where L is the length and G is the acceleration due to gravity. So, longer pendulum means bigger or smaller period? Bigger, okay? Greater acceleration due to gravity means smaller period. So if I have a pendulum on the moon, and a pendulum on Earth, and a pendulum on Mars, it would be longest on where would the period of that same pendulum be the longest? On the moon. It's got the smallest gravitational acceleration, okay? So it would take the longest, right? It'd be weird, but if I had that same pendulum I was swinging there just a minute ago, okay? On Earth, it's going back and forth like this. On Mars, it'd be like, and then on the moon, it'd be really slow, okay? Because it's 1/6 of what it is here. All right. So, period of a pendulum located on a high mountain where acceleration due to gravity is 9.71 meters per second squared. Pendulum is 1.55 meters long. So we're being asked to calculate big T. Okay, so big T is going to be 2 pi times the square root of L over G. Okay, and we get that pendulum would have a period of 2.51 seconds. That's a pretty long pendulum. It's 1.5 meters long. Okay, so it would take quite a while for it to swing back and forth, back to equilibrium one time. Now, some terminology about a pendulum. The weight on the end of the pendulum is called the bob. I don't know why, but that's what it's called. So when you're when you're problem solving, it says the bob takes this long, or the mass of the bob is this much. They don't mean him. Okay. The bob is just the mass on the end of the pendulum, because as everyone knows, watching SpongeBob SquarePants actually makes you dumber. I heard that somewhere. I totally believe it. Okay, totally believe it, because if you live in a pineapple under the sea, yeah, see, now you're gonna have that song stuck in your head. You're so welcome. Okay. I want you guys to try this one. I want you to find the length of a pendulum that will swing back and forth with simple harmonic motion with a period of 1 second on Earth. Okay, so you got to do that square everything manipulation. Okay, solving for L. So for this question, okay, we have to manipulate the formula T equals 2 pi times the square root of L over G for L. So first we square everything. T squared 4 pi squared times L over G. Then to get L by itself, I multiply both sides by G, divide both sides by 4 pi squared. That'll leave me with L. Okay, so that'll be 1 second squared, which is still 1. Okay, multiplied by 9.81, and then divided by 4 times pi squared. That pendulum is just under 25 centimeters in length. All right, everybody okay with those two formulas? They're not too tough to use, right? You can just plug and solve, plug and solve. All right, try this one. Now you're solving for G. So these astronauts take this thing to a planet, okay, and they are looking for the G on that planet. Because I had to square everything. Right? If I want to move or solve for anything that's under the root, I have to get rid of the root. The way to get rid of the root is to square. But if I square this, I've got to square everything in the equation. That's why T comes out squared. Yeah? Oh, I left that recording. Okay, well, there's lots of dead space in this one. Okay, let's have a look at this. So if I want to calculate what G is on this planet, okay, I obviously have to first manipulate this formula to solve for G. So that's going to be first square everything. And then basically cross multiply G and T squared. So G will equal 4 pi squared times L over T squared. So that'll be 4 pi squared times 0.65 divided by 2.8 squared. Okay, so when we punch that into our calculator, 4 pi squared times 0.65, and then divide that by 2.8 squared. Okay, we're looking at 3.27 meters per second squared as the gravitational acceleration, which would make this approximately a Mars-sized planet. Okay, Mars would have 1/3 the gravity of Earth. That's roughly 1/3.
Should we put brackets around the 4 pi squared, or should we just leave it how you did it?
It'll depend on your manipulation, but since I was just multiplying all three of those things in a row, it doesn't matter. You could put brackets around it, get the same answer.
Well, because I put brackets around mine, but I got like 16.7. So wrong. I know it's wrong, but like,
Did you put the squared outside the bracket?
no. Is that why?
Well, I was just, so you typed it in like this, 4
Pi squared.
pi squared, and then
divided
and
times 0.65. Oh, okay. Mine's just weird.
I'm not sure what happened.
Oh, I squared 0.65. That's fine.
That would be why. Okay, so let's look at, we're not going to do that one. Okay, those are waves. We're not on waves. And we're not onto that yet either. So, you know what? I'm going to call up a couple from the digital workbook here because that's what we need. Okay, so you need your digital workbook open here, guys. We're going to look at a couple from there, okay, that are just this stuff. So we're looking at the Unit 4 workbook. Okay, so we should have no problem doing the first, like 10 there. Okay, so they all either use the two formulas we just looked at, or T equals 1 over F, or F equals 1 over T. Okay, that stuff there. All right. Oh, no, hang on. No, we can't get to 10. We can do up to number 7. So let's have a look at up to number 7 for right now. Okay, so we're gonna just kind of quickly look at this whole idea of energy and simple harmonic motion here. Okay, just going to kind of introduce it, and then we'll leave it at that. So obviously, if we're doing work on something, work equals force times distance. Okay, we learned that last year in Science 10. When we're talking about an elastic object, okay, like a spring or a rubber band, okay, we're talking about elastic potential energy. All right with that? Yeah? Okay. So last year in Science 10, you did this lab on work and energy where you pulled a rubber band. You may have had to do it virtually, okay, but there was somewhere in there, okay, where you took a spring scale and you attached it to a rubber band and you pulled it to various lengths. Okay? If you were in my class, you did this lab virtually because I know I recorded it. Okay? I recorded myself, one of the days I was here by myself, pulling on a rubber band with a spring scale over top of a ruler. Okay? And when we did that, what we got was a graph that showed us force and distance. Right? What we saw was that as we stretched the rubber band, the force required increased linearly with distance. Okay? Is that one of the things we said was necessary for simple harmonic motion to occur? That restoring force had to vary linearly with displacement. So this graph kind of holds true with that, okay? But what you were asked to do in that lab was to calculate the work that was done, okay? And you calculated the work by multiplying, or essentially calculating the area under this line, which ended up being the force times the distance, okay? And thus it calculated work, right? Now, when we look at the force that's used to deform or restore, let's say, in simple harmonic motion, that force is actually calculated by taking the spring constant and multiplying it by the displacement, which, oddly enough, we use x for in this unit, not d, okay? And it has to be negative. Right? This here is what we call Hooke's law. You might remember Hooke from Science 10. He's the guy who built the first microscope. He was a physicist. He was just playing around with lenses and, built the most important tool ever for biology. Because, well, physics. They're awesome. Okay? So, he built the first microscope, but he also studied a lot of stuff about springs and elastic objects, and he found that the restoring force, or the force in the spring, is related to the stiffness of the spring and how far you stretch or compress it. Okay? So negative k times x gives you your restoring force. Everybody with me there? Okay. Now, if I multiply that by displacement, okay, I would get work. Agreed? This would be my restoring force. And then if I multiply it by displacement again, I'd get the work. Well, work equals force times distance, which equals negative k times x times x. But on this graph, if I calculate the area of that box, or that, sorry, of that triangle, it's not a box, I have to go base times height over 2. So in other words, it's half of the force, okay? So this is the force here, k times x, multiplied by 1/2 times x again. Okay, so I end up with 1/2 kx squared. That right there is the formula for calculating elastic potential energy. An object's elastic potential energy is the average force multiplied by the displacement. Okay, or 1/2 kx squared. Okay, so that formula is new because we've only dealt with gravitational potential energy, m times g times h. Okay, now we're looking at elastic potential energy. So the stiffer the object, the bigger k is, okay? And then obviously the further you pull it, okay, the more energy you're putting into it. So either the harder you pull it or the farther you pull it, okay, the more energy you're going to put into it because the more work you are going to have to do in order to accomplish that. All right with that idea? Okay, so restoring force varies linearly with displacement. The further I pull it, okay, the harder I'll have to pull, the more work I'll do, the more energy will be stored in the object. Okay? Now, if we go back here just a second to Hooke's law, why is there a negative in there? So Hooke's law calculates the restoring force, the force that's trying to bring the object back to equilibrium. Why does there have to be a negative in that answer? Nope, it's not, doesn't have to do with gravity so much. Let me grab something elastic here. That might be a good idea. Okay. Aim this at all of you. That's a better idea. Okay, so if I pull this rubber band towards me, which way does the restoring force pull? Opposite. I displace it towards me. The force has to be the other direction. That's why this formula has to have a negative in it, because force and displacement are both vector quantities, and I need to make sure that my restoring force has the right vector. Okay, that is that it's opposite the direction I displace the rubber band. I displace the rubber band to my right, so the rubber band has to pull to the left. Restoring force is always opposite the displacement. Okay. Everybody all right with that? Okay, that's as much as I want to go over today. I usually teach this lesson after we go over the unit exam, so it's a little bit short. Okay, which is why we're done a little bit early. But you have a unit exam tomorrow, and you have an assignment due on Thursday, so you got some stuff you could work on. And I'll take questions if anybody has any about stuff that's on the exam or about the assignment or something like that. If anyone has questions, I can answer those right now as well. Okay.